Hello everyone. In this video I wanted to talk about some very basics about RC circuits and especially the three different excitation which are usually we deal with in our circuits. One is the impulse and second is the step and the third is the ramp. Okay, I would like to leave the ramp for you as let's see how it goes. Okay, I will give you a hint about how to approach this. Now the purpose of this video is not to give you the answers, it tell you how you should approach, okay, so that you can use it for many other problems. Okay, first a few points which you must understand is you must clearly understand these excitations. For example, let's understand this impulse. What is the impulse? Let's see this. Let's take this as time t is equal to 0. Okay, it starts at 0 and this is how it proceeds on the right. Okay, so this is the time axis. On the right the time is increasing and this excitation is at 0. So if I take a simple RC circuit, okay, let's not go into complex, you can do it on your own if you understand this. Now impulse is a sudden change. Okay, I'm talking about voltage impulse. Okay, so how can we see this now? It is an impulse, you can see at time is equal to 0, it is infinite. Okay, the height is infinite, the width is 0. Okay, and if I integrate this over this time, the integration is unity. It means the amount by which it is having the height, okay, by the same amount the width is scaled. How to show that? Okay, let me say this height is, let's say this is a square wave. Let me light it clearly somewhere here. Let's try to understand this. Okay, let's say this height is phi. Let's not worry about what scale it is. Okay, just give numbers. This height is phi, and what if this is 1 by phi? What is the width? What is the integration now? If that is 1 by phi into phi, it is unity. Now just imagine what would happen if I go on increasing the height, okay, and proportionately if I go on decreasing this width. It means let's say in this example, so if I make this 1 by 10 and I make it 10, how will this diagram look like? It will look something like this, correct? Now what happens if I go on continuing doing that? Let's say 1 by 100 into 100. What will happen? The area is still unity, but the height is increasing, the width is reducing. So if I continue doing that at infinity, you can expect such a curve. Okay, you can imagine that in your mind. So impulse is such a signal where at 0 the height is infinite but the width is 0, but the area, if I integrate from this point to this point around this, I get unity, just like this examples. Fine. Okay, this is one very important point about impulse. And another thing about impulse is it is existing only at time 0. At any other time there is no signal. Okay, for example, let's say if it is V in, okay, let's just say it is V in. If I make dV in by dt, if I differentiate the signal at different times, okay, at t is equal to 0, if I am going to differentiate this, okay, I get some signal, right? Because there is a change in value. Okay, let's not get into the absolute value, just think of the differentiation as, is there a change in the signal? Yes, there is a change in the signal. There is infinite change it in 0 time. Okay, infinite change in 0 time, so it is a large value here, correct? A very large value. So in such a case, we will see how to analyze the RC circuit. Now at a very long time, let's say somewhere here, what is the differentiation? If I apply differentiation at this point, there is no signal, so the differentiation would be 0. It means if I feed this signal into a RC circuit, or if I excite my RC circuit using an impulse response, the excitation is only temporary at t is equal to 0, and at very long time or any time after this, there is no excitation in the system. The input doesn't change. Okay, the input doesn't change. Remember this very important point. The input doesn't change is a very important point to note. Fine. Okay. Now next, let's talk about unit step response. Okay, or let us try to first analyze what happens if I feed a impulse voltage into a RC circuit. How does the RC circuit respond, or how can I plot, how can I look at this V out now? Okay, now let's feed a impulse. Now see, immediately when I feed a impulse at t is equal to 0, there is an infinite excitation, or there is infinite change in the input with respect to time. So the change or excitation to the system is really high. Okay, so what do you think will be the current now? Let's talk about current. We will talk about the current and the capacitance relation. Remember, the capacitor cannot charge instantaneously. Okay, we must know that the capacitor cannot charge instantaneously, but in order for the capacitor to charge instantaneously, the current must be equal to infinite. Okay, if there is an infinite current in the circuit, then the capacitor can charge instantaneously. The moment you apply excitation, the capacitor will be completely charged. It can charge. Okay, now if you look at this voltage is an infinite voltage, so there will be infinite current. The current initially at t is equal to 0 is infinite. Okay, so there is an infinite current. It means the capacitor can charge instantaneously, and going by the KVL, the maximum voltage the capacitor can reach is equal to V in, is it not? Because this is the V in which I have applied, V in. So what happens is, immediately when you give a signal, let me write like this. Let's say this is an impulse. Okay, if this is an impulse, your capacitor would be instantaneously charged to V in immediately, because there is infinite current. This point must be very clear. The capacitor charges only if there is an instantaneous or there is an infinite current in the circuit. Unless otherwise, the capacitor cannot charge instantaneously. It is not possible. Okay, the second case where it is possible is, let's say I do not have a resistor here. Okay, let's say there is no resistor. In that case also there will be infinite current, because the current limitation comes because of the resistance. Okay, if the resistance is 0, again I can charge the capacitance in 0 time. I can have infinite current and charge the capacitor instantaneously. So for impulse it is happening like that. For impulse, the capacitor is instantaneously, it has gone from 0 and charged to V in. Now what happens after a very long time? Is there excitation in the circuit? No. It means the input is not changing, and if you look at the circuit, the differentiation of the input, it is 0. It means there is no more excitation. So what will happen? There is no excitation, so the circuit will have its own natural response, and it will have to what will happen if the input excitation is 0? We can treat this as short circuit, right? This will be shorted to ground. So the capacitor has a discharge path, so it will slowly from there it will discharge. And what would be the final, after at infinite, what will be the final voltage is decided by, okay, let's say we must comment on what is the final voltage. It can be commented by what happens to the dV in by dt at infinite. It is 0. There is no excitation. If there is no excitation, the final value has to be 0 at infinite, because there is no excitation. The circuit has no work. What I mean to say is, there is no it does not have to respond to any signal now, because there is no signal change. So it will happily go and sit with its own time constant. So this is about the impulse response. So these 2 points are very important. The capacitor charges only when there is the current is infinity, and that happens when you give an impulse. And for impulse, the capacitor charges instantaneously to V in, or whatever voltage you apply here, and then after you remove that, after a very long time, it will settle to 0. It will discharge. So this is the impulse response. Now we apply the same logic to this case. Now let us see what happens to at t is equal to 0 for a step input. For step input, if you see what is happening at t is equal to 0, again we have a change. Okay, let's say this is going from 0 to some v in. But this change also, if you see, there is a change from 0 to v in, and it is happening in how much time? In 0 time. Again, at this particular point, at this particular point, if I ask you what is dv in by dt, that is infinite. It means you're applying infinite change to your system. You're exciting the system with infinite input change. Okay, now the next question is whether the current is equal to infinite. Is the current infinite? If the current is infinite, again the capacitor would be instantaneously charged. So is it happening is the next question. So let me write those diagram again. There is a R, there is a C, and now we have a step excitation from 0 to V in. Now we are monitoring at t is equal to 0. And we know at t dv in by dt at this point is equal to infinite, so we are analyzing this. Okay, now let's say this is the output. We are commenting on vo. So one thing is sure that, okay, let's find out the current now. Okay, at t is equal to 0, dv in by dt is infinite. Okay, at infinite there is infinite change. Now what is the current? At infinite frequency, because the input change is very rapid, the frequency can be treated as infinite frequency, and at that frequency I can treat my capacitor as a short circuit, and this is obviously the ground. So what will be the current now? The input is V in at this point, correct? You have applied V in instantaneously, and the resistance in this path is just R. So the current would be V by R, and this is not equal to infinity. It is not equal to infinity. So can the capacitor charge instantaneously? The answer is no. So it will start at 0. It will start from its initial state and then start charging. Okay, so initially at very high frequency, this is how you will analyze the system. Now what would happen at a very long time? Okay, let's go at this point. At this particular point, sorry, at this point, what if I see what is happens to dv in by dt? Is there a change in the input? No, the differentiation value turns out to be 0. It means that you are not exciting your system with any input change. So obviously it will just has to settle. What do you mean by that? It is just responding to this change, and it is only settling to the final value. And at infinity, at very long time, the input change is 0. It means the capacitor will now charge and finally settle to the input voltage. At infinity, you can expect the voltage equal to V in. Okay, fine. So this is how it works. Fine. The another thing is the the ramp response. The ramp. Now this is very interesting. Part of it I will answer to you, and part of it I will ask you to analyze. And before that I will give you some more insight about this. Okay, see, whenever you give a excitation to the system, or a change to dv in by dt is applied, the circuit with its own time constant, it has to respond to that. Okay, it has to respond to it. For example, here this is the time constant which is deciding the response time. It is responding. Similarly for impulse response, there is a sudden excitation, and then it is slowly settling down to 0. So this settling is decided by the time constant. For this is the settling decided by the time constant. Fine. What do I mean to say is, whenever there is a change in input, sudden excitation, for example this, the circuit will take certain time to respond to that. Similarly here, I suddenly excited it at 0 time, and then I left it, so it is responding to it. It will take its own time. Okay, so what do I mean by that is, if there is a change in the input, the circuit based on its own time constant has to respond to that, and that is decided by the circuit time constant, that is the product of R and C. Now for this particular very interesting case, if I take t is equal to 0, if I differentiate it, okay, if I differentiate it, it's, and if I take t is equal to infinite, Oh, sorry. Okay, at t is equal to, let's say, at a very very long time, let's say somewhere here. Just give me a minute. Mm, okay, there's some problem with the pen. Okay, fine. So if I differentiate this at a very long time, is it finite or is it zero? For a ramp, the differentiation value here and the differentiation value here, the excitation. What do you mean differentiation? What is the change in the input? Here also there is input is changing, here also input is changing. It means at infinite also there is a constant excitation. You are constantly exciting the system. Okay, it means the circuit will require some time to respond to it. It cannot respond to it instantaneously because it has its own time constant. And also we know that for this case, one hint is, can there be an infinite current if you apply this type of signal? No, the answer is no. So I is not equal to infinite. It means the capacitor cannot charge instantaneously. So it means now next question is is it a charging type of waveform or discharging? Obviously, because input is rising, the output also will rise, so it is charging. So capacitor is charging. Okay, so it will charge based on its time constant, so it is limited. The charging is decided by the circuit's time constant R into C. So you are applying dV in by dt here and it will respond to that. You are applying dV in by dt here, it will respond. So you are applying constant change at every time. It means the circuit, what, for example, let's say I feed some signal here and it will respond after certain delay. Let's say that delay is some tau. Then you apply another signal here, it will display plus some tau. What does it mean now is, actually you are doing a change in the signal at every time and the circuit requires its own time to respond to that. And let's say that time constant, the time is fixed, right? Because the time constant of this is R into C. It means that your input, if I would say this is the input excitation, your output will not be responding immediately to those points. It will take certain time because it has its own time constant. It means it will not respond here, it will start somewhere here. Okay, okay, so this response will come here. Now this will start responding. Okay, so if you see, there is a constant difference. Why this is constant difference? How to look at this now? To look at this, you can simply take it as a circuit which is having certain time. For example, what happens, if there is a machine here, okay, if I put, let's say there is a, this is a conveyor belt, okay, this is a conveyor belt and there is a block, and the speed of this block is such that in 1 minute it will take this box from here and throw it in this box. Okay, so after 1 minute you can expect this box to come and drop here. It means if you put another box here, it will also take another 1 minute. Okay, now if I put a box pipeline here, every box will take this much time delay, this much time delay to drop into this box, is it not? And what is this time delay in the constant, or in the context of this circuit? The RC time constant. So you apply the input, but you can expect the output after some time. So it means there will be constant delay, and this will be decided by the time constant of our circuit. So that's about the way of analyzing your circuit in terms of impulse, step response and ramp response. Okay, so I would just repeat the points. Always analyze your circuit for two things. You have to check for dV in by dt at 0 and dV in by dt at infinite, and always check whether there is a infinite current or there is not. If there is no infinite current, remember the capacitor cannot charge instantaneously. If there is a infinite current, the capacitor will charge instantaneously. Okay, and always try to find dV in by dt at infinite, and then you can decide how will be the final response of the RC. I hope these points were clear. If you still have any doubts, you can drop in the comments, and based on this particular guidelines, you can take complex circuits and try to solve on your own. Okay, I hope this was helpful. If there is any question, please drop in the comment section. And to support our video, please do subscribe and share it with someone who may find it useful. Thank you.